Hello again, everybody. My name is Pixel Rain, or Rain for short, and today we're going to be adding some noise to our voxel generation. So we have a lot of ground to cover today, so let's say goodbye to our little blue metropolis here and let's get started. The first thing I'm going to do, because it bothers me, is I'm going to create a scripts folder and move our existing scripts into that folder, just for slightly better organization. And then the next thing we're going to do is we're going to create a new class called indexed array. And the purpose of this class is to be the container we use to store our voxels. And let me double check. Oh, I still have namespaces. So the purpose of our indexed array class, as I was saying, is to replace our dictionary. And we're doing that because I've decided to use compute shaders to generate our noise instead of using good old CPU processing. So you can't pass a dictionary to a shader, so we have to use a flat array, as decided here. And I'm going to be skimming through a lot of the files today because there's a lot of changes here, so I'll just briefly touch on, the different points of it. So inside this essentially wrapper class, we're just creating a new array of size, either container size by max height, which we'll get to in a second, or something like that. So we're just going to be doing an array that's 16 by 128 by 16 wide, so it'll be a fairly large array, but all we're housing is single integers per block, so it's not too bad. We're going to have a nice little function to get an integer coordinate from a vector 3, which just uses this handy little bit of math. We've got a nice clear function in here that just sets every block in the array to a default, which in the case of our voxels will be ID 0. Then we've got our handy accessor, same as in container, just because I'm lazy and I don't want to type the extra variable, and it already gets kind of messy in this video. So that is our indexed array. The next thing we're going to do is we're going to convert our voxel to an integer because, like I said, we're using compute shaders and we won't be able to pass a byte to a compute shader. It is not a blittable type, so we have to use an integer, which sucks because that's 4 bytes instead of a single byte. The next thing we're going to be adding back in here is I made a little class, let me fix my spacing here, a little class called world settings. That's just going to be used as a static reference within our world manager, just to make accessing it a little bit easier. So we'll have a public non-static variable, and then in our start method, we'll assign our static method or our static variable to be our publicly visible one. And the next thing we're gonna do, actually, because I think we can go ahead and, no, we can't start that yet. The next thing we're gonna do is we're gonna come back to our project and we're gonna make another new class. This one will be called Compute Manager. And this class is going to run all of our compute shader related code because it gets messy. So this one, again, I will briefly touch on, and I'm skipping around a little bit in my projects here. Let me just clear this out. That looks correct. Okay, so the point of this class is to act as an object pool for structs that I have here called noise buffer, and eventually we'll have one for a mesh buffer, more than likely. And so to do that, we have a list and a queue holding our noise buffers. And when we start, which is what this function here is, let me rename that to initialize just for clarity's sake. Change that call. Ooh, I don't even have that call over here yet. Let me add that. Yeah, instance.initialize 1. So during our initialize, we set two integers x thread, y thread to be the result of our chunk size divided by 8, because when you run compute shaders, you want the number of threads that it's dispatching to multiply against the number of threads in the compute shader. Bad explanation, I know, but essentially we want to do 3 times 8 in the compute shader to give us 24, and then 3 times whatever this is to get 128, so that we have our total chunk size being generated. Now, I know I just said 24, but there's a reason for that, and it's because when you use a compute shader, you have to have the correct number of threads per, essentially in this case, voxels we want to generate. So 16 by 128 by 16 would be what we'd use. But to fill the seams around our chunks, we have to overshoot that. So we want to generate like 2 blocks out traditionally from our 16, so that we can create an overlap between chunks without actually overlapping. Here we set our integers, bools, whatever you have for our actual noise generation itself. So I assign the container size from our world settings, some options in the shader itself, the world height, the scales used for the noise and thresholds, and then our surface ID and subsurface ID for the blocks we want to place. Right now that'll just, go to our colors. And then we've got the pooling functions down here. We've got our get noise buffer, which checks if we have any available in the queue. If we do, return it. If not, create a new one. And then we have that function, which just creates a new buffer, initializes it, and passes it back. And we've got a function to clear and requeue a buffer. So if we're getting rid of a chunk, it's not being rendered anymore, we can clear out the data that's on it and put it back in our available queue. And then we've got our compute shader helpers, which is what I use to dispatch the shader without having to manually write this out everywhere it's used. So all this does is assign our buffers to the shader. So we'll have a noise buffer, which is our voxel array, and a count buffer just to keep count of active voxels, so anything solid. That's more than likely going to be important when we get to trying to do this with meshing, but not really used right now. Then we set our chunk position and the seed offset, because in GLSL you can't, or at least I haven't seen it, where you have a seed set for your noise like you do traditionally. So what I do is I generate a random position based off that seed that you provide, and then pass that in so it moves the chunk by, negative 10,432 by 0 by negative or positive 88,400. It just generates a random offset to it, so it gives the effect of having random noise. And that might change later. This is just, first draft of noise. Then the biggest time saver here is Unity's new Async GPU readbacks. So usually you would call buffer.getData and then pass that back into wherever you're storing it, so like our array. That will lock up your mainframe until the shader itself is done running and it's come back. We don't want to do that. We don't really care if it takes a little bit, so long as it comes back to us eventually. So what this does is, as soon as it's ready, whether we're on the main thread or not, or I think technically it runs on the main thread, but it notifies us wherever we're at that it's done. Here's your data, and then we can call our new render mesh function off our container, which will generate the mesh for it. We've also got a clear voxel data that just dispatches a second kernel to wipe out the array, make it all empty. Some safety features for the buffers, just when we quit, dispose all the buffers, and then our actual buffer itself contains 2 compute buffers, 1 noise, 1 count, and then our indexed array. I'm going to be moving that out of container and into this buffer, so we aren't reinitializing a 16 times 128 times 16 array every time you make a new chunk. I'd rather you pull the data from a pool. We initialize it here, clear out the data in the noise buffer because sometimes you copy data over. It's a little weird. And then the actual dispose function. So if it's not null, we call dispose on the buffer. And then The only other thing that happens CPU side will be changes to our container here. So we're going to start up here at the very top. 1 second, I'm working off 2 code bases here. We're going to replace our dictionary with our noise buffer that we were just talking about. And we'll populate that by calling our get noise buffer from the queue. And then we'll change our clear data to use that clear and requeue buffer. Not that we're calling this function yet anyway, but might as well have it set up. And then I've added a new function render mesh, and that way it can just trip off both of these once we've got the noise data back. And I've also moved mesh data.clear data here because this will be the last time we're running on the main thread until we get to uploading the mesh. So we want to make sure we have our mesh data cleared out before we try to generate a new mesh over the top of it. And you can't access mesh, like mesh, the Unity struct itself from a background thread. And then we're also going to change our for loop here. So we'll do a 3-dimensional for loop for x, y, and z. And our x and z is going to start at 1 and continue to 16. So technically that's 17, but you know. And we do that so we don't draw our first block because we won't know what's behind 0. But we'll draw our 17th block or our 16th block, which will be that 0 position of the next chunk. So it'll fill in our seam all the way around and make it so we don't have giant cracks in our terrain. Down here, we can get rid of our contains keys because we aren't using a dictionary anymore. Don't actually need empty voxel down here either. And the only other change we need to make here is in our upload mesh, we want to make sure we're setting our index format to unsigned int 32 so we can go beyond that 65,000 vertice limit that's traditionally in our meshes. Now let's see if we have any errors so far. I do indeed. Ah, right, there we go. All right, so we're going to make our container public. And we can go ahead and get rid of this stuff. And all we're going to be calling now is computemanager.instance.generate voxel data, referencing our chunk. And I'm sorry, we don't actually need this right now. Yeah, so referencing the chunk, I don't know if I've explained that before, but because container is a class, if we were to pass it in normally, it would essentially create a copy and pass it into that function. When you reference it, you're doing just that. You're only referencing where it's at in memory, so you're not reallocating the entire thing. So that should be everything for the CPU side. Let me make sure that's cleared out all our errors here. It has. That's a good sign. So now we're going to go ahead and create a new folder called compute shaders. And we'll create another new folder in that called noise. And I will tell you right now, I absolutely did not find, or I did not write this noise implementation myself. I am not that good at math, nor do I think I will ever be that good at math. But I will post the GitHub where this came from online. It is just a simple simplex noise implementation for GLSL. It does 1-dimensional, 2-dimensional, 3-dimensional, and 4-dimensional noise. And then we're also going to go ahead and create another script called height map noise. And this is the script we use to actually generate our voxel data. I'll change this to compute because Unity won't let me create CG inks inside of Unity. And then here we've got a struct representing our voxels from the outside so that we can take in a structured read-write structured buffer of voxel, which you saw passed in Compute Manager. And all of these options you also saw passed in during the initialization right here. So this is where they're going to. And then we've got our not so fancy math that takes in our container size and returns an coordinate and returns an integer. And then the actual function that makes all this work is just this little bit of code. So if our position provided by our thread number and some other math that I don't remember off the top of my head, if our x and z is greater than container size x plus 2, so if we're doing a 16 by 128 chunk, if it's greater than 18, we want to return. Because if you'll remember at the beginning, I said we're actually running this 24 by 128 by 24, just so we can get those extra 2 voxels. It's ridiculous, but that's how it has to be with compute shaders. And then this function is just a basic height map function with a cave generator built in. So we set up our position by our ID or index, our chunk position, and our seed offset. Then I take the two-dimensional version of that by taking pauses x and z, and I generate a height through our simplex noise, multiplying it by noise scale. So we're looking at 0.001, 2, 3, 4, and so on instead of 1, 2, 3. And then you multiply that by the max height. So between 0 and 1, which is the result of the noise, we'll multiply that by 128, and that'll give us a nice range. It's not going to be anything spectacular right now. It's just going to be some rolling mountains and whatnot. But the benefit of doing it on a compute shader is we can make our noise much more complex without affecting our overall performance that much. I don't know if you've ever tried to run mathf per lin in octaves, let alone a 3D noise implementation, but it's pretty bad. Anyway, we convert the height to an integer so we can actually compare it to our position. And if the y is greater than our rounded height, we make it air, and then anything below that will probably be solid. If the block is within 3 blocks of the surface, we'll make it that surface voxel ID that we assigned, so 1 in this case, and then if it's not, we'll make it 2. And if the bool for generate caves is enabled, we'll run a 3D noise function that if it returns a value greater than 0.8, that's what the threshold is set to right now, we'll make it air, so it'll create little pockets and stuff in the world. I've also got a function in here to force the floor if the y position is 0 or 1, just because the caves will produce holes into the void, and you usually don't want that, but there's an option, you know. We also increment our counter if it's a solid block, and then we assign it back to our array. Sorry if you can hear my dogs, they're getting excited. And then we will go ahead and assign our compute manager to our world manager object and our shader to it. Go ahead and set up our colors here real quick. Do a nice green and a dark brown for the sublayer. Make that 2 with the smoothness of 8. Make that 6 with the smoothness of 2. And let's see if I messed anything up. Only slightly. Alright, so the one thing I forgot to do here is over in our container, I want to go ahead and we're going to add a new function right about here, actually, called check voxel is solid. All this function does is check if our point is within the bounds we've set here. So if it's size plus 2 on x and z or negative on y. If it is, we want to return true so we don't draw that face. So if this is the edge of the chunk, we don't draw the exterior face. If not, we return the voxel's value at that position. And then we just want to change our face check to be that function. Same thing as before. And now we should be able to run this and see our little piece of terrain. Hey, look at that. It doesn't look like anything. But a handy thing about using dynamic sizes is that we can change the size. So now you can see we have a little piece of mountain with a hole cut out. Nothing too impressive, but we can make it bigger. Takes a second. Now we've got a little valley cut out between some mountain ranges. As you can tell, this terrain isn't the best looking. I'm not super efficient with noise, but I will try to refine the actual noise soon. If anyone has any comments on that, let me know. And that'll be it for this episode. In the next episode, we'll be looking into threading, which I've got a sneak peek of that'll play in a second. Alright, and here's that preview of our threading from the next episode. This is 64 by 64 chunks being rendered, and of course I've have the world selected, so that's slowing down the editor. But as you can see, no seams. In the next video, I'll go over how I did this and how we can change our little world to be that. And then in the following video might get even more complex. I'm not 100% sure what order I'm going to do it in. I hope everyone is enjoying this video series so far. Let me know in the comments if you have any questions or suggestions, and don't forget to subscribe. It really helps out being a small channel, and I'll see you all in the next video.